Hello everyone, this is Dr. Webb. In our last video, we talked about doing double integration over rectangles, and that was very nice. You know, if we have some rectangle where the bottom is talking about x values going from a to b, the y value was talking about y values going from c to d, and we have some function over this. You know, we could get this nice integral. Say if we wanted to integrate it in terms of x first, the x values are going from a to b, and the y values are going from c to d. Remember, the inside integral goes with the first d, with the first variable. The outside variable goes with the y, and so in this one we'd be integrating x first, and then we'd be integrating in terms of y. And then with rectangles, we saw we could actually swap this, and swapping this was very easy. And so now we're integrating in terms of y first, then in terms of x. So these connect. The c and the d are talking about y. The a and the b are still talking about x. And so this was very nice. Not too difficult to do. Basically, you're just doing two regular integrals. But, you know, not all regions on the xy plane are rectangles. And so what if instead your region looks like that? How do you set the integral up for that? Where this is, the bounds here are not, you know, so nicely drawn in terms of a and b and c and d. Okay, so this is the focus of this. Okay, so we're talking today about double integrals over some region R on the xy plane. Right, and so R is some region. We're looking down on the xy plane, so there's our axes, there's R. This dA here, this is called an area measure, and dA here is either equal to dx dy, if we're to integrate in terms of x first and then y second, or dy dx, and it just, which one it is, just depends on what we're integrating first. But really deep down, when we think about dA, so dA is coming from a limit of these delta A's, and these delta A's are still rectangles. They're little rectangles, delta A, where the width is delta X and the height is delta Y. And so dA, delta A, when you take the limit as delta X and delta Y goes to 0, delta A turns into dA, the delta X turns into dx, the delta Y turns into dy. And so this is just a way of saying this is how we're integrating it, the whole thing, without saying necessarily what order we're doing it in. Okay. So the name of the game for this video is starting off with an integral like this in its general form, and then trying to figure out how to write it in a way where we can actually evaluate the integral. And so there's going to be two types of regions that we think about. First one we're going to think about are what we're going to call type 1 regions. And so what a type 1 region is we can, for the x variable, we can define the region for the interval. There's an interval for x where all the x values stay between a and b. And so let's draw this out. So on the x-axis, there's an a and a b. And then in terms of y, we have two functions. We have an f of x, and then we have a g of x. And so the y values stay between these two. And so the region as a whole is between f of x and g of x, and where the x values are between a and b. Okay, and so the bounds in x are from a to b, and then for any x value in between a and b, we can draw a straight line ahead, line above it, where f of x is on the top and g of x is on the bottom. Okay. Now the way that we are going to treat these integrals is we're going to integrate these type 1 regions. These are going to be, we're going to integrate y first. Okay, and the thinking is that since if we fix an x value, the y values are going between two functions, f of x and g of x, well, we can integrate on that line. So first what we're going to do, first integrate on that vertical line above x. That's going to get rid of the y's, and then we can just integrate all the x values we get from that from a to b. Okay, and so the way that we're going to write that, the way that we're going to show that we're doing that, is we're integrating y first. The bounds for y, these are functions that contain x in them, and it is okay if we're integrating in terms of y for the inner integral to have x's in them, because then they will flow in and go into our integrand. And then after we evaluate this, we'll be left with a function that just involves x's. And so after doing this first inside integral, we're left with a function of just x's. And so then we have some, at the end, we have some integral from a to b of this function that's just x's in terms of x. And so this is a doable definite integral then. Okay. So let's do an example to walk through this. So we're going to evaluate the integral x squared times y over the region R, where R is the region between the parabola 4 minus x squared and y equals 3x, where the x values range from 0 to 1. So first let's draw out this region. So 4 minus x squared, that's a parabola pointing down, like so. It's almost an accurate picture. And then we have y is equal to 3x. And so that's going to be a line of slope 3 going through here. You can check that these two are going to hit each other when x is equal to 1. Right. If I plug in 1 to 4 minus 1 squared, I get 3. 3 times 1 is 3, so they are hitting there. And so this is at the point 1, 3. And our x values, so our x values are going from 0 to 1. And then for some x, let's put, there's 0. For some x in between here, the region is between the line and the parabola. Okay, so the region overall is this almost triangular shaped region here. It would be triangular if it wasn't a parabola on top. And for each x value, we're integrating from the line y equals 3x to the parabola. Okay, so the way that we're looking at r here is our x values are going from 0 to 1, starting at x equals 0, going to 1, and then for some x value in between, the y values are starting when we hit the line. So the y values are starting at 3x and going up until we hit the parabola. So 0 to 1, x is going from 0 to 1, and y is going from 3x to 4 minus x squared. Okay, so now let's draw out what this is going to look like. So our integral is going to be, so let's do the inside integral first. So we're doing x squared y. We're integrating, since we're integrating up this vertical line, so going up on a vertical line means that we're doing y first. And the bounds for y are going from 3x to 4 minus x squared. And then we're integrating in terms of x, and the bounds for x are from 0 to 1. It's important to note that in the outside integral, my bounds are just numbers. There's no variables in there. So when we are done evaluating that, there will be no variables left over. Everything will be worked out, and we'll have, this is a definite integral, we will have a real number answer coming out of this. Okay, so this is our integral. So let's do the inside integral first. So we're integrating in terms of y. So the integral of x squared times y in terms of y, the x squared is a constant. Integral of y goes to y squared over 2. And then we're evaluating this from 3x to 4 minus x squared. So then what is this going to look like? And so then after we do this, we're then going to plug this into the outer integral, 0 to 1 dx. So we have 0 to 1. These bounds are what we're plugging in for y. So we have 0 to 1 x squared 4 minus x squared squared over a half minus x squared times the quantity 3x squared over 2. And then we're doing dx. And so let's multiply this out. 0 to 1 of, I'm just going to pull, everything has a 1/2, so I'm just going to pull that 1/2 out. I have x squared times 16 minus 8x squared times x squared gives me 8x to the 4th plus x to the 4th times x squared gives me x to the 6th minus 9x to the 4th dx. And so minus 8x to the 4th minus 9x to the 4th. Let's simplify that down to 17x to the 4th. Yeah, we used up that 9x to the 4th there. Okay. And now this is an honest to goodness Calc 1 integral in terms of x. So we can just do it out. So I have 1/2 16x cubed over 3 minus 17x to the 5th over 5 plus x to the 7th over 7, with our x values going from 0 to 1. If I plug in zeros, everything disappears. And so this is left with 1/2 times 16 over 3 minus 17 over 5 plus 1/7. Whatever that is. Okay. So this is an example of a type 1 integral. So this is a type 1. And in type 1, you integrate y first. Okay. So as opposed to a type 1 where you integrate y first, we've come up with a really clever name for the other type. It is called a type 2 region. And so in a type 2 region, the roles of x and y are switched. Right? So if we're drawing out the region, so now y, we have nice bounds for the y values that appear. Okay, and then in between those y values, we have two functions of x is equal to a function of y. And so r of y looks something like that. So remember, this is x is equal to a function of y, so rather than going from left to right, really they're going kind of up and down. So s of y maybe looks like that. And so our region here looks like so. And the idea here is that if I take some y value between c and d, I can draw a nice horizontal line across that goes from the inside r of y function here to the outside s of y function there. And if you try and do vertical lines here, you can't necessarily get from one side to the other without going in and out of the region. Whereas all of the horizontal lines here, any way you go across, they will stay in the region the whole time. And these horizontal lines will cover up the entire region. Okay. So when we integrate this, the way that we're thinking about integrating this is you fix a y value this time, and then integrate over the x values first. And so you can imagine that it's for some fixed y value, we're integrating over all the x values, so we're integrating this time over the horizontal line first. So we're going over horizontal line first. And then once we've done that for every y, then we just add those up for all the y values. And so lastly, then we're adding up all the y values, so then we're just going from c to d. Okay. So when we write this, you can see we are integrating in terms of x first, where our inner bound is the r of y and the outer bound is s of y. And then after we've done that, then we're going to be left with a function that's just in terms of y. And so because we're going to integrate y second, it's okay to have y values in the bounds here, because then when we do the second integral in terms of y, those are all going to be taken care of, and we're going to end up with an honest to goodness number. Okay. So let's do an example going through this. Okay, so in this case, we're evaluating y minus x over the region R, where R is between the curves xy equals 1 and x plus y equals 5 for the y values 1 to 3. Okay, so let's first try and draw this. So one thing about this example is we don't have the functions written nicely either as y is equal to a function of x or x is equal to a function of y. It's sort of, at least these two functions are left a little bit nebulous. You can do either one you want. So xy equals to 1, that's a hyperbola. That's kind of going through like this. X plus y equals 5. So that's y equals 5 minus x. And so if I take 5 here, it's going to go down slope 1. And so then we're doing this for the x values for the y values starting at 1. And so that'd be kind of going across there up to 3, going across there. So this is our region. Okay. Now this is an example of something that is definitely a type 2 region and not a type 1 region. If I pick some y, I can go across any y value between 1 and 3. I can draw a nice horizontal line that goes from the hyperbola on the inside to the line on the outside. If I try and do vertical lines, sometimes on the vertical line I hit the hyperbola and then I hit this horizontal line. Sometimes I hit a horizontal line and then another horizontal line. Sometimes I hit a horizontal line and then I leave on the slanted line. So there's not one function that's always above and one function that's always below. There is always one function that's to the left and one function that's to the right for any y value. And so that's what's telling us that this is a type 2 function. So my region here, our y's are going from 1 to 3, and then our x's, the inside function is, well, I want to take xy equals 1 and write it as x is equal to a function of y. So solving for x here, I'm going to get x is equal to 1 over y. And since the hyperbola is the inside function, I have a 1 over y there. And then for x plus y equals 5, that's my outside function. Again, I want to solve for x. So I'm going to write this as x is equal to 5 minus y. So that's how we're treating the region. And so then our integral is going to look like y minus x. We're going horizontally, and so we're integrating the x's first. My bounds are functions of y. And then after that, then we're integrating in terms of y from 1 to 3. Okay, so first we're integrating in terms of x. And so y minus x integrated in terms of x is going to give me y times x minus x squared over 2. And my bounds are x is going from 1 over y to 5 minus y. And then we're going to plug this into our other integral. Okay. So I got to plug these bounds in. So plugging in 5 minus y in for x, I'm going to get y times 5 minus y is 5y minus y squared minus 5 minus y quantity squared over 2. Then this is all subtracted by plugging in 1 over y. So y times 1 over y gives me 1 minus 1 over 2y squared dy. So let's see, we should do the 5 minus y squared. That's going to be 25 minus 2y plus y squared. So let's put that in. this is 25 minus 10y plus y squared. Okay, so then I have 25. 25 over 2 I can't do anything with. But then I have minus 10y over 2, but it's minus minus. I already have a 5y. So those two, we're going to have to erase our region here. I'm sorry. Let's write this out nicely, what we have. Okay. Let's finish this up. 1 to 3 of, I'm going to have 10y. Then I have minus y squared minus another y squared over 2 is going to give me minus 3 over 2y squared. And I have minus 25 over 2, but then I have another minus 1 over here. So minus 25 over 2 minus 1 is going to give me minus 27 over 2. And then lastly, I have minus 1 over 2y squared. So 1 over 2y squared. And now we're doing the integral in terms of y. So integrating this in terms of y, I get 5y squared minus 1/2 y cubed minus 27 over 2y plus, so this is really 1/2 y to the minus 2, which would give me minus, integral of that would be minus 1 over y. Minus 1 over 2y. And now we're doing this from 1 to 3, and so then that's just plugging it in. So we'd have 5 times 9 minus 1 is 8, minus 1/2 times 27 minus 1 is 26, minus 27 over 2 times 2, minus, so I'd have 1/6, and then lastly plus 1, whatever that big beautiful number is. Okay, so that is integrating a type 2 region where we did x first. And so horizontal line. Okay. So if you get a region that neither fits nicely into either a type 1 or a type 2, what do you do with it? Well, if you can't write it as either of them as is, then what you have to do is you have to cut it up in some way and break it down into smaller regions that do fit nicely into them. As our last example, we're just going to set up this integral. We're not actually going to work it out, but we're just given the region that we're just given that it's enclosed by two curves. And so what we're going to do is we're going to look at this region and figure out, can we do it as a type 1? And if so, set it up. And then can we do it as a type 2? And if so, set it up that way. So let's draw this out. So we have y is equal to 2x squared. So 2x squared, so that is a hyperbola going up like roughly like so. And then we have y is equal to 8x. So that is a steep line of slope 8. Okay, we can see these two intersect twice. One intersection is at the origin, 0, 0. If you plug 0 in for x, you get y is equal to 0 for both of them. The other intersection, if you set 2x squared equal to 8x. Divide by 2, you get divide by 2, and also we're looking for the one that's not 0, so we also can divide by x, and we're left with x is equal to 4. Okay, so this other one is occurring at x is equal to 4, and so plugging 4 into one of these, this is happening at 8 times 4 is 32, and so this is at the point 4 comma 32. So as you can see, this picture is incredibly well to scale. Okay, so that's our region. Let's blow this region up a little bit more, a little bit bigger over here. So the line is up there, and then the parabola is through here. Okay. So can we do this as a type 1 region? Can we do this as a type 1? So remember, for type 1, we're thinking about picking what are our x values that are going between. So our x values here would be going from 0 to 4. And then if we pick some x value between 0 and 4, do we get a nice vertical line? And if we change that x value, do we always have the same function on top and the same function on the bottom? And looking at this in this region, yes, we do. Right? So if I fix some x value, what do my y values do? What happens along that vertical line? Well, I start off at the parabola. So my lower function is the parabola 2x squared, and I keep going up until we hit the line. So our upper bound is 8x. Okay. So how do we draw this as a type 1 region? So for the type 1 region, we're integrating in terms of y first. And so y would be going from 2x squared to 8x of our function 3y. And then we're putting dy in there to indicate that we're integrating in terms of a vertical line. So in terms of y first. And then after we do that integration in terms of y, then we're doing the integration in terms of x from 0 to 4. Okay. So that's what we get treating this as a type 1 integral. Well, can we also treat this as a type 2 integral? Well, let's get rid of this vertical line. Well, so what are the y values in the region here? Well, it's starting at the origin, so the y value there is 0, and it goes up until we hit the point, and so the x value there was 4, the y value there is 32. Okay, so our y values are going from 0 to 32. Now, if we fix some y value in between and draw a horizontal line across, is there always some inside function that we hit first and some outside function we hit first? And if you draw horizontal lines across, yes, there is. So this means, since we're doing this about a horizontal line, we're going on a horizontal line, we're going across x values. And so the inside function that we're hitting first is always the line. But we want to write this line now as x equals something in terms of y. So rather than y equals 8x, we want to think about it as x equals y over 8. And then we keep going until we hit the parabola. And so the parabola we have as being y is equal to 2x squared. But we want to rewrite this, solving for x. And so we have y over 2 is equal to x squared. And so then we're taking the square root of that. So in terms of x, this side of the parabola, we can write it as x is equal to square root of y over 2. Okay. And so as a type 2 integral, so type 2, we're taking our function and we're integrating in terms of x first. So our x bounds would be y over 8 to the square root of y over 2, integrating in terms of x. And then after that, we integrate in terms of x. Then we're integrating in terms of y, 0 to 32 dy. And so that's how we can represent this integral as in terms of y. In terms of a type 2 integral, where we integrate first in terms of x and then in terms of y. Okay. So, if you really need to evaluate this, the nice thing about being able to do it both ways is then you can look at the two individual integrals and say, which one would I rather do? Which one would I actually want to work out? In this case, I don't think there's that much of a difference between them. Actually, for the bottom one, for the type 2 integral, even though there's a square root in those bounds, when we integrate y, we're going to get y squared, and then you plug in the square root, that's going to cancel off. So that square root is not going to hang around. So it's really kind of personal preference from here, which one you would actually want to do. That is all I have for you right now. I will see you again soon.